Hi everybody, welcome to the next part on Multimediale Werkzeuge. This time more about wavelets in JPEG 2000 and quantization. So unlike JPEG, where the DCT was fixed, JPEG 2000 gives us a certain choice for the wavelet decomposition to be used. So it's not only the wavelet filters that we saw the last times, but we also have more choices. One possibility is the so-called Haar wavelet, which is basically a 2x2 DCT and has this following transform matrix. It's very simple, so it just consists of 1s and -1 and has this factor of 1 over square root of 2. And the inverse is basically the transposed one. Yeah, so the low-pass impulse response for the analysis and synthesis is the first column of the transform matrix. So here, this first column is the low-pass filter, which is the same for the analysis and synthesis. And for the high-pass, we get this for the analysis, so basically this column here. And for the synthesis is simply the reversed version, right? So, but very similar. So the Haar wavelets have the advantage that they are easy and efficient to implement, but have the disadvantage that the resulting filters are not particularly good because they are very short. Right. So also note that here for the high pass we read from bottom to top, which is actually also the case for the low pass. But there it doesn't make any difference because it's the same. Right? So in general, if we read out filters from the transform matrix, remember we start from bottom and go up. And this reversal is not true for the synthesis, and that's why we have this change in direction. Yeah, so this is a disadvantage of the Haar wavelet. The advantage is they are really easy to implement. Yeah, so they do not have much attenuation between the subbands. We have relatively much crosstalk between the subbands. Yeah, to solve this last mentioned problem, we can also apply longer wavelet filters, which we already saw. In JPEG 2000, the so-called Dobischi's 9,7 filter pair is mostly used. And these numbers, they refer to the length of the filters. Yeah, so the impulse response used for the analysis are the following. Here we have the low-pass filter again. We have this impulse response of length 9 for the analysis. Here you can see it. So we already saw it. You can see it again. And the corresponding frequency response that we already saw can be computed and obtained, for example, by applying a DFT or FFT, which has been previously set to a length of 512 by appending enough zeros, for example, because this gives us the number of frequency samples in our frequency response. The magnitude, it's not amount, but magnitude of the frequency response can be then seen here. So here we have the magnitude, and we can see this is the pass band, which looks quite nice. Then we have a relatively wide transition band, and then we get relatively high attenuation here, close to Nyquist frequency. Here we have Nyquist. Yeah, so horizontal axis represents the normalized frequency, where here 1 is Nyquist, half the sampling frequency. Yeah, so strictly speaking here it would say times pi, so pi would be corresponding to the Nyquist frequency. Yeah. Let's see, we see that we still have to multiply by pi for the normalized angular frequency, which means pi corresponds to Nyquist and 2 pi to the sampling frequency. So this is the usual use of normalized frequencies, to use pi as the Nyquist frequency and 2 pi as sampling frequency. So for example, we have a screen or display with a resolution with a spatial frequency of 10 pixels per degree. This corresponds then to our sampling frequency, right? We sample our screen. Our Nyquist spatial frequency, not local but spatial, is then 5 periods per degree, or brightness cycles per degree, because we always need one bright and one dark line. So if we have 10 pixels, then we have 5 pairs of dark and bright. In normalized spatial frequency of 0.88, where we have an attenuation of minus 40 dB in this diagram above, which means we have an attenuation factor of 1/100th, 0.01, corresponds to a spatial frequency then of 0.88 times 5 is 4.4 periods per degree back on our screen. Right. So suppose we have brightness fluctuations of 4.4 periods per degree with a brightness amplitude of 10, meaning fluctuations between, for instance, 45 and 55, then the amplitude after filtering is only 10 times 0.01 equals 0.1, and we only have a brightness swing between 49.95 and 50.05, right? So here this should be brightness. Yeah, so this is now in the invisible range. So before, the contrast was enough for us to see a fine pattern, right? So just assume it's enough. And after this, it's so little that we don't see it anymore. The pattern, the fine pattern, became so weak that it's now invisible and we only see it as a gray surface. Yeah, so these high spatial frequencies are suppressed in this way. Yeah, so here you can see minus 40, going back to this plot here. Here we can see minus 40 dB. Here passband is 0, minus 40 dB, which corresponds to 1/100th. And here we can see it's roughly 0.88. 0.88 times Nyquist. Yeah. So our passband ranges from the normalized frequencies 0 to 0.5, and 0.5 here corresponds to 0.5 times 5 equals 2.5 periods per degree in the example. So again, assuming 10 pixels per degree, that means our Nyquist frequency is 5 periods per degree, and that means 0.5 relative to Nyquist corresponds to 2.5 periods per degree in this example. So this would be our passband. Goes from 0 to 2.5 periods per degree. Yeah, and here you can also see how we then convert from our normalized frequency range to our frequency range of our display and a given viewing distance, right? We have pixels and viewing distance gives us the angle. Yeah, here in comparison, the Harlow pass filter with only two coefficients. So here the impulse response basically has just two ones followed by zeros, and the resulting frequency response is this. So here it's now not normalized, but here we can see the subbands coming from our DFT. Right. So we chose a DFT of size 512. That means 512 corresponds to the sampling frequency, and 256 corresponds now to our Nyquist frequency, which is right around here. And here you can see we don't have much attenuation. So passband here is around maybe 6 dB plus. So, and if we want to achieve minus 40 dB, then we have to go from plus 6 minus 40 would be like 34. So here in this range, and 34 is already really close to Nyquist. Right. Or the other way around, if you look at normalized frequency 0.88, 0.88 corresponds to 0.88 times 256. So then we come to subband 225. So then we are in this range here, and then we only get about minus 40 dB, 14 dB attenuation. Yeah, so not against, but compared, or relative to frequency 0. Yeah, so here we can also see that only the highest frequencies have useful attenuation. Yeah, the corresponding high-pass filter, H1 for the analysis for the Dobie-Schiess filter, has this impulse response, so it has length 7. Right, remember low pass was length 9, and here we have length 7, so that's why we get this name 9,7. So you can see it has more changes in the sign, which is a typical sign for a high pass. And here's the resulting frequency response. So it pretty much looks simply like the flipped version of the low pass. Right now here, this is the pass band from 0.5 to 1. And then here we have our transition band, and then close to DC we get very high attenuation. And this is important for images, because this is where images have the highest energy, and having the high pass, having high attenuation close to DC, avoids this high energy spilling over into the high band. Yeah, and this is important for compression performance, so this high attenuation. Right, avoids crosstalk to the higher band. And this is achieved in the filter by having as many zeros as possible at frequency 0 in the z-plane. So the z-plane is what characterizes a signal or a filter in the z-domain. Right, remember the z-domain from Grundlagen der Videotechnik, and this is what we get if we apply the z-transform to this high pass. Right, so when we apply it to this high pass, we get a polynomial in the z-domain, and this polynomial has zeros. Remember, every polynomial has zeros in the complex domain, and it has as many zeros as the order of the polynomial. And you can see, since we have a polynomial of order 6, we have 7 coefficients. The first starts at 0, so we have order 6. And we see we have 6 zeros. We have 4 zeros here at real 1, and then we have 2 additional zeros here. And the frequency response can be estimated or guessed from looking at this z-domain plot by seeing this unit circle around the origin. Right? This unit circle corresponds to z equals e to the j omega. And if we plug or replace or substitute z by e to the j omega, then we obtain the discrete time Fourier transform, which we use for obtaining our frequency response. Right? So remember, the DFT is simply a finite length version of the DTFT. So it's basically what we use to obtain our frequency response. So then frequency 0 means e to the j omega equals 0, means real 1. So this is 1. This is frequency 0 then. And e to the j omega equals pi means Nyquist. And remember, pi in radians gives you this point. So then here at this point we have the Nyquist frequency. And if you go on to 2 pi, we get the sampling frequency. Then we just continue here and we land back at frequency 0. So basically one cycle gives us all possible frequencies. Yeah, and that means if we then start at omega equals 0, then we see our polynomial has 4 zeros. That means it's 0, right? If we go a little bit up, then we have a small distance to all those zeros. That means we have the small values to the power of 4, and that means it's still very small. And this is how we get a very high attenuation close to frequency 0, because we have 4 zeros here. Yeah, and this is one of the characteristics of this filter. Yeah, so here's the Z-transform. So if you don't remember, this is how it's defined. So basically we just take our sequence of coefficients of our filter from the impulse response and turn it into a polynomial. And this polynomial has zeros. Yeah, so here if we replace z by e to the j omega, then we get the frequency response. Right, so we have 4 zeros of the transfer function, and therefore we get a very high attenuation near frequency 0. And this is how in principle these filters were designed. So what do the corresponding synthesis filters for the decoder or synthesis look like? For the synthesis low pass, we get the following impulse response. So now we can see here on the synthesis side, the low pass is shorter. It has only 7 tabs or coefficients. And the corresponding frequency response actually is quite similar to the one in the analysis. Almost no difference. So again, normalized frequency 0.88 gives us an attenuation of about minus 40 dB. And then for the high pass in the synthesis, now this high pass is longer. Now it has 9 coefficients or 9 tabs. And the corresponding frequency response again is very similar, almost no difference. Yeah, also has a good attenuation at frequency 0. Yeah, and the analysis and synthesis filter bank in direct cascade should reconstruct the original signal perfectly. So here's the analysis. Now we have one stage for the rows, and the following stage is for the columns. So each is one-dimensional. This filters along the rows, and then the result is taken, and we have those filter pairs along the columns. And for the synthesis, we get the reverse structure. So we simply use each pair here for the reconstruction, upsampling, and again high pass and low pass. And then we do the same for the rows. So upsampling is done by insertion of a 0 after each sample, and then do the filtering. Yeah, and in this way we can undo the cascade step by step. Note that undoing does not work without delaying the signal. The downsampling, upsampling, and filtering includes a delay that must be taken into account when reconstructing unfiltered branches, right? Inserting an appropriate delay to compensate is important, because remember, the higher branches are not further decomposed, they stay, but the lower branches, the lower frequencies, they are further decomposed, and that means they will also get a corresponding delay. So we need to compensate for that. Yeah, so here are the coefficients listed numerically, basically for copy and paste for your own experiments. So here you can say copy and then paste it in your Python code. Here's the high pass analysis filter. Here's the low pass. Here's synthesis, low pass synthesis, and here's high pass synthesis. Yeah, and finally quantization. In JPEG 2000, we do not have a fixed quantization matrix as in JPEG with the DCTs, but the encoder can select the quantization step sizes relatively freely. The quantization step size is then transmitted to the decoder as a site information. A step size is provided here for a subband or for the entire picture. Right? So we say we have this quantization step size for this subband, and this is then valid for the entire picture. In this way, we have a relatively high flexibility in the encoder, so that the encoder can select the step size best suited for the image or the desired quality. The aim is to minimize the bitrate and the visible artifacts. Okay, and that's it for today. Thank you for your attention and see you next time.